In this work, we present a method of real-time path planning for an airbrush robot with a single movement axis. This robot is handheld, and therefore the user is in control of the robot's position. When the robot is passed over a target region, the robot must use its single axis of movement to place as much paint in the target location as possible. Our contribution is to design a method that can run in real time whilst considering a long time horizon to enable paths that are close to optimal. The method starts with quantizing the space defined by time and gantry position into a grid. On this grid, a directed acyclic graph is formed in a manner that ensures the change in speed at each node is acceptable. As you can see from this simplified example, the head cannot transition from going full speed one way to full speed the other way. Next, at each grid location, we sample the amount of paint required on the geometry if the head were to be in this location at this time instant. The result of this sampling process is shown by the white shapes in this image. The green lines in this image represent a simplified version of the directed acyclic graph. The cyan line is the path selected by our method in this case. The weights for the graph are calculated from the required paint map. If this calculated flux for a line segment does not overdose the geometry at this location, it is given a score proportional to the paint required at this location. The directed acyclic graph is now solved with Dijkstra's method. This finds a path that is most likely to provide a fruitful opportunity for the nozzle to place paint in the target location. Only the first line segment is converted to a motor command for the robot. We now simulate the first line segment in a dense manner. At each time instant along the path, it is decided if the nozzle should be active at this location or not. These nozzle timings are uploaded to the robot to control the air valve for the airbrush. The internal representation of the paint coverage is updated to include the paint dispensed in this line segment. Now the process can repeat for the next line segment. Here is a preliminary demonstration of the method in use on a prototype robot. In the bottom right, we can see the proposed plan for the next second of time overlaid on the required paint density. Next to that is the current paint distribution on the geometry taken from the simulation. Only the relevant parts of the texture map are shown. You can see that although the robot is being maneuvered by hand, the robot will move the head in such a way to maximize paint landing in the target regions. This shared control method means that the user does not need to know the detailed shape of the target region. We compared our method to an exhaustive path evaluation and found that on average it picks a path in the top 15% of all paths. This plot shows 32 different scenarios. For each, the method was used to find a path, and this path was given a rank out of all possible paths. For clarity, they have been sorted into ascending order. We compared our method to a greedy algorithm that simply picks the best line segment available to it after each move. Interestingly, the greedy method performs worse than picking a random path. In conclusion, we have demonstrated an effective algorithm for path planning for a shared control painting robot. This work could be useful for developing an accurate liquid dispensing system where automatic positioning on a large scale is not feasible.